Okay, so let's do a half-life problem. Um, Here's one. So this is actually in section 4.6. Um, there should be a C14 example somewhere. Well, this is number 17 in section 4.6. We're not going over section 4.6 like specifically, but this is just a nice problem. So the half-life of radium-226 is 1,600 years. So, in other words, if you've got like 10 grams of radium-226, after 16 years, you have half of that left. Right? So you'd have 5 grams left. And the remaining 5 grams, the 5 grams of radium that's gone, decays into something else, depending on what the radioactive isotope you're dealing with is. All right, so radium-226 is this many years. How much of the samples? This is parts C and D. So part A will say, so apply. Let me tell you the half-life formula. So the half-life formula is as follows. The amount left after T years is equal to, so the amount of the initial sample. So I, amount of the initial sample, and then 1/2 to the T over H, where H is the half-life in years, and T equals the number of years. Right, so for every number of half-life periods that you go, it's reduced the initial sample by a half. So 1 half-life period, so I mean, if the half-life is 1,600 years, 1,600 over 1,600 is a half. 2 half-life periods, 3,200 over 1,600 is 2. So that gives you 2 half-life periods at 3,200 years. So the initial sample is then reduced by half, and then reduced by another half. So half of a half is a quarter. So on and so forth. For 4,800 years, that's 3 half-life periods. The amount left is half of a half of a half, which is an eighth. So you have the initial sample over 8, so on and so forth. So that's just for half-life periods, years and half-life periods, but that works for any number of years. Okay? So in this example, let's answer the following questions. A, so apply the half-life formula to our example for radium 226 with an initial sample of 22 milligrams. B, how much actually this is C. In the book, it's C. How much of the sample will remain after 80 years? And D, after how many years will the sample decay to 2 grams? Two milligrams. So we, is it milligrams or grams? We're doing here. No, I'm looking at the wrong problem. After 4,000 years, and 18 milligrams remain. Okay, so for part A, right, the amount after T years is 22 milligrams is the initial sample times the exponential function 1/2 to the T divided by 1,600. So that's the half-life formula for our example here for the cesium-226 with an initial 22 milligram sample. C, how much of the sample remains after 4,000 years? So after 4,000 years, the amount that's left over is 22 times 1/2 to the 4,000 over 1,600. So this is equal to, so 1/2 is 0.5 to the exponent 4,000 divided by 1,600. So 1/2 to the 4,000 divided by 1,600 is this 0.17677, but I'm going to multiply that times 22. So 3.889 milligrams. So is that about right? Does that answer make sense? How many half-life periods is 4,000 years, approximately? So, right, there's 4,000 years, and each half-life period is 1,600. So this is 40 over 16, right? So that's 20 over 8, which is divided by 4, 5 divided by 2. So this is 2.5. Right, so 2.5 half-life periods. And every time you do one half-life period, you reduce the sample by 1/2. So during the first 2 half-life periods, you reduce by 1/4. 1/4 of 22 is 5 point something. Right? 1/4 of 22 is 5, well, it's 11 halves, 5.5, right? 5.5 milligrams. And then one more half-life period takes you from 5.5 to 3.9. Okay, so that's about right. That's about right. Intuitively, it's right. And then D, this is D. The more interesting question is the following. After how many years will the sample decay to 18 milligrams? So you know that the sample is 18 milligrams. You mean you look at it, you measure it, and somehow you measure it and you see, well, I got 18 milligrams of cesium-226. And somehow I know I started out with an initial sample of 22 milligrams. Okay, how you actually know these things is a complicated question for chemists and physicists and people who study these matters. But the mathematics they use to then date such a sample is exactly this. All right, so you have 18 milligrams left. You started with 22. And now, how many years have gone by? Solve for t. Okay, so now you're just wondering how many years have gone by. And this is the exact calculation that you've done. How you measure what you have and what initially there was, you can't always measure them precisely, but you know, people who study these things have ways of measuring them. Okay, so divide both sides by 22. So 18 over 22 is equal to 1/2 to the t over 1600. I divided both sides by 22, right, so that I isolate the exponential function. Now that I've isolated the exponential function, I want to apply the log to each side to get the t exponent out of the exponent and down, down below, so I can solve for t. So apply whichever log function you want. We'll take log base 10 this time. So 1/2 to the t over 1600. All right, so the exponent t over 1600, the exponent inside the log comes out as a coefficient. It's again applying this. Right, the natural log of a to the r is r times the natural log of a. It's the same for the log of any base. It's the same for the log of any base. So, when you're doing such equations, when you're solving such equations, you can apply natural log or the common log base 10. Alrighty. So we bring that down. So this is log 9 over 11. So that's t over 1,600 log of 1/2. So now I'm going to multiply both sides by 1,600. T times log 1/2. Divide both sides by log 1/2. And that's equal to t. So, that's the answer, but of course we would like a decimal approximation so that we have some idea about how many years we're talking about here. Okay, so let's do that. So this is a little bit more complicated. Let me do this one in a browser. So, my keyboard. So we've got 1,600 log 9 over 11. Divided by log 1/2. So this is how it interpreted the input, and it's fine that the 1,600 is here. It doesn't have to be on top. It's the same thing. And here they're saying log x is a natural logarithm. It doesn't really matter because you can use it. Let's see, log base 10, see if it understands it that way. Ah, it did. Okay. And what did we get? 463.21 years. So 461. 463.21 years is approximately t. Okay, so that's the mathematics that you use to actually do this radioisotope dating that you hear about every so often. The popular one that you hear about is the carbon-14 dating, but that one's actually not that accurate because it's hard to know what what the initial samples are. Sometimes it's hard to know whether or not samples have been contaminated over 10,000, 20,000 years. It's a difficult one. There are other ones that are much more accurate because you can know what initial samples were and that there is no contamination, with a high degree of certainty. And that's what this uranium U-235 dating, but that's only useful in certain situations. Anyway. So that's the mathematics that goes into it. The science is a lot more complicated, but we're not getting into that. All right. So that's a lot of examples of equations that have exponential expressions in them and how to solve them and where they're applied and so on and so forth. So there are, of course, also equations that have logs in them that you would like to solve. Let's get a couple examples of that. So equations. So solve the following equation. With a log expression. So log of 5x plus 2, and when I write log without the base, that means log base 10, right? Log, that means usually log base 10, although Wolfram Alpha seems to call it the natural log. And ln means log base e, where e is that Euler's constant. So anyway, this one, log of 5x plus 2 is equal to 2. So solve for x. Okay, so remember, okay, the log of 10 to the log base b of b to the x is equal to x, and b to the log base b of x is equal to x. In other words, log and exponential functions with the same base, they're inverses of each other. So in particular, log of 10 to the x is equal to x, and 10 to the log of x is equal to x. And these are specific examples leave out the base there. The log of a to the r is equal to r log of a. So these are specific examples, specific instances of this basic identity here. The log of a to the r is r times log of a. So anyway, what you want to do in this kind of situation is not apply the log function to each side of the equation, but apply the exponential function to each side of the equation. Which exponential? Whichever one you like. To each side. Exponential function base 10, exponential function base 2, exponential function base e, whichever one you like. Here, this is log base 10, so we might as well use 10. So 10 to the log 5x plus 2 is equal to 10 squared. Well, 10 to the log of whatever is just whatever. 10 to the log of a is a. In this case, a is 5x plus 2, and 10 squared is 100. So log base 10 works out nicely here because, you know, it cancels out and I don't actually have to use this. I'll redo the example with a different base. But, you know, you come out with the same answer. It doesn't matter how you do it. So 5x equals 98. So x equals 98 over 5, which is what? So 95 is 19 and 3/5. Okay, so 19 and 3/5 is 19.6. All right, so that's using the base 10. Let's try a different base. Let's solve again using base e. Okay, doesn't matter which base you use, but let's do it with base e. So log of 5x plus 2 is equal to 2. So e to the log of 5x plus 2 is equal to e. Oh, no, I'm sorry. No, you have to use the right base. I apologize. No, you have to use the right base. You have to use base 10 in this instance. So whatever the base of the logarithm is, that's the base you must use in solving such equations. So let's look at a different example with a different base. How about natural log solve for x? Natural log of x plus 2 plus the natural log x minus 1 is equal to 1. Okay, so remember natural log is log base e. So you want to apply the exponential function to both sides of the equation, or, you know, after some work or something like that. Let me show you a couple different ways you can solve this one. So first of all, let's apply e, the exponential, base e, to both sides. Equals e to the 1. Right, so this log x plus 2 plus log x minus 1 equals 1. So e to the log x plus 2 plus log x minus 1 equals e to the 1. Remember also, whenever you have e to the a plus b, this is equal to what? What was the basic identity that you can use when you have a sum in the exponent? Remember, this is e to the a
times e to the b.
Times e to the b. E to the a times e to the b. So this one is e to the natural log x plus 2 times e to the natural log x minus 1 equals just e. Well, e to the natural log of x is just x, because the exponential function, e to the x, and the natural log x are inverse functions of each other. So this one becomes x plus 2. This one becomes x minus 1 equals e. So this becomes x squared plus 2x minus 2 equals e. So this is a quadratic polynomial, but it needs to be set equal to 0. So I'm going to move the e to the, well, let's not do that. How about, what if we put a 0 here? This is e to the 0, and e to the 0 is 1. Remember, e to the, a to the 0, whatever the a is, that's always 1. All right, so natural log x plus 2 plus natural log x minus 1 equals 0. So you apply the exponential to each side, you get e to the 0 here, but that's 1. This is a quadratic equation, but you have to have it set equal to 0. So this becomes x squared plus x minus 3 equals 0. This one does not factor, so we'll just apply the quadratic formula. So b squared plus 4ac over 2. So x is equal to minus 1 plus the square root of 13 over 2, or minus 1 minus the square root of 13 over 2. Okay, so whichever base it is that the logarithm is using in your equation, that's the base of the exponential function that you have to use to solve it. Okay, so here we had to use base e. Here we had to use base 10, or this one right here. So that's different with equations with exponential expressions. There you can just apply any log that you'd like. So here's another solution. This same problem here. So remember, the natural log of a times b is the natural log of a plus the natural log of b. Right? Not the natural log of a times b is natural log a times natural log of b. It's the natural log of a plus the natural log of b. It's like this thing here, right? That the e to the a times e to the b is e to the a plus b. It's sort of the equivalent formula to this here. Oops. Erase that. So let's apply that in this case. So here we're doing it in reverse. So natural log x plus 2 plus natural log x minus 1 equals 0. So this is natural log x plus 2 times x minus 1 equals 0. So natural log x squared plus x minus 2 equals 0. Now we'll apply the exponential function to each side. So now e to the natural log of x is just x. So in this case, by x, I mean x squared plus x minus 2. This one is 1. So x squared plus x minus 3 equals 0. And then as before, we have that x is equal to, what was it? 1 minus 1 plus root 13 over 2. Or minus 1 minus root 13 over 2. Well, actually, this one is not a solution. because this is a negative number, so natural log of x minus 1 is undefined. So this is the only solution, right? The original equation has natural log of x minus 1. Now, if I plug in a negative number for x, and then I subtract 1 from it, it's still going to be negative. The domain of a logarithmic function is just all positive numbers. You can only plug in a positive number. You can't even plug in 0. No zeros, no negative numbers. Right? So in this case, right, the solutions to this quadratic equation are minus 1 plus root 13 over 2 and minus 1 minus root 13 over 2, but this number doesn't work in the original equation. So down here, same thing. Okay. Time we got 10:32. Let's look at some problems in the text here. So I assigned from this section, well, actually I didn't assign any of those, but we'll try a couple of them. How about number 63? So solve for x. Log base 2 of x plus log base 2 of x minus 3 is equal to 2. Okay, so similar to the problem that we just did, right, you can take the log base 2, the sum of the two log base 2's, and multiply their arguments. So this becomes log base 2 of x times x minus 3 equals 2. So log base 2 of x squared minus 3x equals 2. Because this is log base 2, the exponential function that you have to apply is the base 2 exponential function. So 2 to the log base 2 of x squared minus 3x is equal to 2 to the 2. So b to the log base b of x, the exponential and the log cancel each other out, being inverse functions of each other. So we have x squared minus 3x equals 4. That's a quadratic equation. So setting it equal to 0 on one side. Now we solve in various ways that we know how, either quadratic formula or by factoring. I believe this one factors x minus 4 times x plus 1 equals 0. So x equals minus 4, or sorry, x equals positive 4, or x equals minus 1. But let's go back to the original equation. You can't plug in the negative number into, well, this one or that one. Right? So in the original equation, log base 2 of x plus log base 2 of x minus 3 equals 4. X equal to minus 1 is not in the domain. of the two log functions. All right, we can't plug in x equal to -1 here or here because log base 2 of -4 is undefined, as is log base 2 of -1. But the 4 is fine. Log base 2 of 4 is 2, and log base 2 of 4 minus 3 is 0. So that's the answer. This one doesn't work. All right. Are there any other interesting problems among these? Oh, how about 61? So solve for x. 4 minus log 3 minus x is equal to 3. So what should we do here? Any ideas? Any ideas what we might be able to do here? I mean, judging from, what we've done on these last few problems here, in particular like this one. Right, in this problem, we have log base 10 of 5x plus 2 equals 2. So we applied the base 10 exponential function to each side. And then 10 to the log base 10 of 5x plus 2 is just 5x plus 2 equals 100. And then you solve for x. So using that idea, what could we do here?
Apply it to both sides.
Yeah, we could apply the exponential to both sides. Actually, it would work just fine. I was thinking to solve for the logarithm first. Somebody typed in a comment. Move the 4 to the right. Either way would be fine. Yeah. So let's move the 4 over, first of all. Well, actually, what I'm going to do, I'm going to move the log over and move the 3 over here. So 4 minus 3 is log of 3 minus x. So 1 is log of 3 minus x. So 10 to the 1 is 10 to the log of 3 minus x. Right? 10 to the 1 is just 10. 10 to the log base 10 of 3 minus x is 3 minus x. So this gives me x is equal to 3 minus 10. So x is equal to -7. Is that in the domain of the original function? Can I plug in x equal to -7 here? X equal to -7. So 3 minus -7 gives you 10, which is a positive number. So that's fine. Like if it was +7, no. 3 minus +7 is -4. So that wouldn't work. But it's not +7. It's -7. So that's one way to do it. Someone else was just saying, well, just start off by taking both sides of the equation as exponents for base 10 exponential function. That works too. Okay, what you need to do here, though, is to apply the, 10 to the a plus b is equal to 10 to the a plus, or not plus, times 10 to the b. So right here, so if you're going to take that approach, then you have to use this. So this becomes 10 to the 4th times 10 to the negative log 3 minus x equals 10 to the third. So in order to deal with the negative exponent, so this is 10 to the fourth and 10 to the third. So I'm going to divide both sides by 10 to the third. Or 10 to the fourth. I'll divide both sides by 10 to the fourth. All right, so over here we get 10 to the negative log 3 minus x is equal to 10 to the third over 10 to the fourth is 1/10. Now, in order to deal with the negative exponent, you have to rewrite it with a positive exponent. Remember, when you have a negative exponent, you move that expression to the other part of the fraction. If it's in the denominator, you move it to the numerator. If it's in the numerator, move it to the denominator. And then you make the exponent positive. Is equal to 1/10. Now, 10 to the log base 10 of 3 minus x is just 3 minus x. You can't apply that here. Right? 10 to the log base 10 of whatever is equal to whatever. But if you've got the negative in there, not quite. Okay, you would need to make the exponent positive, and then you could apply this. So 1 over 10 to the log base 10 of 3 minus x is 1/10. So 1 over 3 minus x is 1/10. Cross multiply. So then x is equal to minus 7. That one didn't work out quite as well as the previous one, but it worked nonetheless. But I think probably this is more generally the way to go here. Seemed it worked out much easier here. Right here, things seemed a lot more complicated, but it still works. Alrighty. What else? So this is interesting. Numbers 69 through 76. Let's look at some of those. Not all equations in which log and exponential expressions, or not in which contain log or exponential expressions can actually be solved algebraically. In particular, equations which mix logs, exponentials with polynomials. So, for example, number 69, natural log of x is equal to 3 minus x. It doesn't help to do this. e to the natural log of x is equal to e to the 3 minus x, because then that just becomes e to the 3 minus x. And this equation and this equation are, just as unsolvable. So we're mixing in a log function and a polynomial. Here we're mixing an exponential function and a polynomial. We're asking, well, when are they equal? Okay, you can't solve that algebraically. Okay, the only thing you can do, essentially, I mean, there's more sophisticated ways and less sophisticated ways about trying to solve such a thing. All you can ever get is an approximate solution. So we can get approximate solutions using computational tools. So, for example, Wolfram alpha is a nice one for this kind of thing, if it ever comes up. So solve x equals e to the, what was it, 3 minus x? 3 minus x. So what is it telling us? Here is the line, and this you can do on your graphing calculator. Here is the line 3 minus x, the blue one. That's the line that's the line, x. Right, so we're comparing the function f of x equals x and the function e to the 3 minus x. So here's the line y equals x. Notice that the scale on the x-axis is different than the scale on the y-axis, and that's why the line is pretty flat there rather than 45 degrees. But the blue line is the function y equals x. The pink one here or purple one here is the function y equals e to the 3 minus x. And they meet somewhere, right there. Okay, and, well, it approximates that as 2.20794. So let me actually copy this, stick it in here. Resize that. Whoops. Whoops, it didn't show me the bottom line there. Why not? Oh, no, I don't have. It's on the bottom, it's on the top. So this is the graph of y equals x and y equals e to the 3 minus x with intersection point shown. And the approximate solution is x 2.20794. Although that's not an exact number, it's just a decimal approximation. And by the way, you'll notice that it says something kind of funny here. X is equal to capital W of e to the third, which is approximately this 2.20794. What's W? WZ is the product log function. I don't even know what that is. Essentially, in order to try to solve these oddball type equations that you can't solve algebraically using common functions, so common functions like logs, trigonometric functions, polynomials, square roots, all the things that you deal with in a college algebra course or in a calculus course, these are just basic or common functions. Sometimes there's also these hyperbolic sine and hyperbolic cosine functions that are also used. But there's no real reason in general to restrict your attention to just those functions. So one common area of research is what's known as special functions. And people define these special functions in various ways. And they study the properties of these functions, just like what we're doing here. We define this log function, we study the properties of log functions, and we solve some equations with log functions. Okay, well, somebody somewhere thought up of this log product log function or whatnot. And, they started studying its properties, and now it's a known thing to them. So folks who like this area of special functions. It's not my area of research, but a lot of people, do work in that. And there's tons of special functions with all kinds of cool names and neat definitions. I do know some, just not that one. Okay, so that's all for today. This is all the material for the course. We've finished everything for the course. So tomorrow we're going to start doing some review. First, we'll review for the exam on Monday. Right, so exam 3 is on Monday, covering these sections. So I'd like to start going over some problems there. If you have specific problems you'd like to go over, please come prepared to ask about those. And then after we take the exam on Monday, we will start reviewing for the final exam on Thursday. Okay? All right, everybody, have a good day. I'll be in my WebEx room at 11:30 if you want to come and see me.